probability part 4, exercise 13.1. In the previous class, we were doing question number 13. Okay. So almost we have finished. The last part was left. You can try yourself. That part. Now question number 14. Given that the two numbers appearing on throwing two dice are different. Given that, find the probability of the event that the sum of the numbers on the dice is 4. So total number of in throwing two dice, the total number of possible outcomes are 6 raised to power 236. Correct? Given that the two numbers appearing on throwing two dice are different, so that is our F. The probability of the event sum of the numbers on dice is 4. So E we have to find. E is the event where we are getting the sum of the numbers. Sum is 4. When we are getting sum 4, that is event E. So therefore event E will have the outcomes 1, 3, 2, 2, 2 plus 2, 4, and 3 plus 1, 4. So 3 possible outcomes are there. The number of possible favorable outcomes to event E is 3. And F is the event which is having the different numbers appearing. So different numbers appearing, you know that only if you will write 36 numbers, 36 possible cases, here you will get 1, 1. Then in the second row, you will get here 2, 2. Like this, you will get up to 6, 6, correct? So only these 6 are having the same numbers on that. So you have to just remove these 6. So how many are left out of 36? If you will remove 6, so total number of cases will be 30. So therefore number of favorable cases to F will be 30. So if you want, you can write the 30 cases. But you need to know the intersection of E and F. E intersection F, because different 2, 2 will not come. 2, 2 will not come in F. 1, 3 and 3, 1 will come. So therefore there are 2 cases only. So E intersection F will have only the 2 outcomes, 1, 3 and 3, 1. Okay, got it? So now you can find the probability of E when F has occurred. Probability of E intersection F means number of favorable cases in, or you can write P E intersection F divided by probability of F. E intersection F means intersection has 2 by 36 2 favorable cases, and F has 30 favorable cases. So 30 by 36, 36 cancel, 2 by 30, that is equal to 1 by 15. Okay. Take the snapshot. Question number 15. Question number 15 is, consider the experiment of throwing a die. Okay, if a multiple of 3 comes up, throw the die again. So what will be the sample space? So the first condition, they are saying that if a multiple of 3 comes up, multiple of 3 is 3 and 6, then again throw a die. So if multiple of 3, suppose 3 comes, so we will throw again die. So we can get 3 1. Possible cases are 3 1, 3 2, 3 3, 3 4, 3 5, and 3 6. And then again, if we are getting second multiple, what will be the second multiple of 3? 6 only in die 6. So if 6 is coming, again throw another die. 6 1, then 6 1, 6 2 are possible outcomes. 6 2, 6 3, 6 4, 6 5, 6 4, 6 5, 6 6, 6 5, and 6 6. Okay, then continue it. If any other number comes, if any other numbers other than 3 or 6, that means it can be 1, 2, 4, 5. It can be 1, 2, 4, 5. If any other number comes, then you have to toss a coin. So let's take 1. Suppose 1 comes, then we will toss a coin. So tossing coin, then head can come with 1 or tail can come with 1. Then if 2 comes, then we have to toss a coin. So 2 head, 2 tail. Then 3 is not here because multiple of 3 we are not taking. Then 4 can come. So 4 head, 4 tail. Then 5 head and 5 tail. So how many outcomes now? We have 20 outcomes here. 6 4, 6 4, 10, 20. So total possible outcomes are 20. So here it is necessary to make the sample space. Otherwise, it's difficult to find out the number of possible outcomes. Okay. Now E, when we have to recognize the event E whose probability is to be found out, and the given probability is for F event. So E, find the probability that of the event coin shows a tail. So E is the event in which the coin shows a tail. So coin shows a tail. So when tail will come, that outcomes, we can take the outcomes where the tail comes. So 1 with tail, 2 can come with T, 2T, 3 will not come because die is thrown, 4 and 5. These are the cases in the event E. So number of favorable cases to E is 1, 2, 3, 4. Only 4 cases. Now F, the event which has already occurred, that is given that at least one die shows a 3. At least one shows 3. And it can be 2. So one die shows 3. Here 3, 3, 3, 3, 3, 3. And one more is there. This one is also there, which is showing 3. Other than that, no one is showing 3. So these all will come here in the outcomes of event F. F is what event? You should write that at least one die shows the 3. At least one die shows a 3 number. So 3 1, 3 2, 3 3, 3 1, 3 2, 3 3, 3 4, 3 5, 3 6, and one more is there, 6 3. So 7, it will be 7. So total number of favorable cases will be 7. 2f. So nf is equal to 7. Now find the probability of E when f has already occurred. The probability of E intersection f, yes. Intersection also find out the intersection between E and f. There will be no intersection, I think. E intersection f is 0, yes. So E intersection f is equal to 0. Therefore, probability of E intersection f upon probability of f. So when there is no event, the probability of E intersection f will be 0. And probability of f, sorry, not E. Probability of f is 7 by 20, but 0 upon anything is equal to 0. So the answer is 0. Question number 16, okay. Here values are given. PA is equal to 1 by 2, PB is equal to 0. Then PA when B has happened. Find this value. So as you know, PB is 0. Here 0 will come, and whatever PA intersection will come, it doesn't matter, but it is divided by 0. So the answer will be infinity. Therefore, answer is C, not defined. Answer is C. Similarly, question number 17. A and B are the events such that, yes, P A when B has happened equal to P B when A has happened. Then if you will solve this equation, this will become P A intersection B divided by PB is equal to P A intersection B or B intersection A, same thing, divided by PA, and these two will cancel. PA will be equal to PB. So it is only possible when two events are equal. So PA is equal to PB. So answer is D. Our answer is D. So that's all for this exercise. Now we will start the next part. So now we will see multiplication theorem. So as you know that multiplication comes when we have to find the probability of two events with AND. So AND shows multiplication, that we know already. But now it depends on the type of event, dependent event or it is independent event. So dependent event, what are dependent events? In which we are taking out the things or we are taking the cards or something without replacement. Without replacement means 1 second occurrence of the second event depends upon the first. So this is in the question, it will be written that without replacement. Without replacement. Or independent, either it will be written it is an independent event, or we are taking the two cards, drawing the two cards with replacement. So you should understand this is independent event, because dependent and independent will have a slightly different formulas. For example, I think we have seen in the starting, if we have to take the two cards, drawing two cards from a well shuffled pack of a 52 cards, drawing two kings, suppose, drawing two kings from a well shuffled pack of 52 cards. Here also we are drawing two kings from a well shuffled pack of 52 cards. Same thing we are doing here, but here without replacement, here with replacement. So that probability of two kings will be equal to what? There are, how many kings are there? First, we will take out of 4 kings, correct? 4 kings and 52 cards. Out of 52 cards, 4 kings can be selected by 4 ways. Total number of ways are 52. Then for taking the second king, first king we cannot be replaced back. So now we have 3 kings to be selected in the second time. And second event is depending on the first. That's why it is called dependent event. So second time we will select 3 out of 51. Correct? Got it? But here, if you are going to select the 2 kings one by one with replacement, so 4 kings you can select out of 52 kings. Again, you have to mix that king and then again select the king out of 4, and total cards are 52. So therefore, if this is these are the two events A and B, so therefore here we can use the formula P A intersection B is equal to probability of A, first probability of A, this is the probability of A. Then second is the probability of B. This is what? This is very simple. Just writing, we are writing like this, so it becomes complicated, but it is very easy. Second is the second event. B is again selecting the second king. So in second king, selecting second king, A is already selected, so that is the probability of B when A is already selected. So therefore PA intersection B will be equal to PA into PB when A has occurred. And this is the same formula that we studied just in the previous exercise. We studied what? PB when A has occurred, PA intersection B divided by probability of A. So this will multiply here. So therefore, PA intersection B will be equal to PA when PB has VB when A has already occurred. Are you getting? So this is, these are the two events without replacement. But whenever it is an independent event, then it is not changing. So simple multiplication. So if you have to find PA intersection B for independent events, so our next exercise is based on all independent events. Okay. So this shows that A and B are independent. If PA into PB is equal to PA intersection B, means this is the condition for independent events. Okay. So, and if you have more than 2 events, suppose you have to find P A intersection B intersection C, then this will be PA has occurred, P probability of B when A has occurred, then into probability of C when A intersection B has occurred. Like this we can write. Okay. And in this case, if you have to find the probability of A intersection B intersection C, it will be a simple multiplication because these are independent event. P A intersection B intersection C will be equal to P A into P B into P C. Okay, so got it. So we can say that from multiplication theorem, we got the result number 1, PB when probability of A B has happened is equal to P A intersection B that we have seen just now. Second condition, PA intersection B can be written as PA into probability of B when A has happened. It can be B when probability of B and probability of A when B has happened. Probability of A and B when A has happened first. Okay. So it depends on the happening. So first into second, or you can say probability of first event into second event is probability of first and probability of second. So like this, or we can remember by first event intersection second event will be equal to probability of first event, that is better, is equal to probability of second when first has occurred. And the fourth is if you have three events, probability of first event, then second is happening, and then third is happening. So in this case, you can write probability of first into probability of second when first has happened already into probability of third when first intersection second has already happened. So like this you can write the formulas. Got it? So this is the multiplication theorem. So independent, what are independent events? Independent events can be defined as, we can say that independent events two events are independent if their occurrence is not affecting to others, occurrence or non-occurrence, occurrence or non-occurrence of one does not affect the occurrence or non-occurrence of other. So one, they are not affecting to each other, whether occurrence or not occurrence. For example, tossing a coin twice. So event of occurring of head in the first throw and occurrence of head in the second throw are independent events. Tossing a coin, if coin is tossed two times. So first time occurrence of head in the first time, okay, it can come in any way, and second time of occurrence will not affect on the first time of occurrence. So that is called if we are throwing twice, so the event should not be affecting to each other, then they are. And in a question you will find for independent events, I told you with replacement or repetition. With replacement or with repetition will be given in the question, then you can easily understand these are independent events. There is okay, so we can have some questions from our textbook now. 13.2. If PA is equal to PB, find PA intersection. We already given that this is a these are independent events. It is already given. And PA is equal to 3/5 and PB is equal to 1/5. Okay. Find PA. If they are independent events, as we know that A and B are independent events, so PA intersection B will be equal to PA into PB. So full exercise is based on the independent event actually. So 1/5. So 3/25. So very simple. Two cards are drawn at random without replacement. I told you, with replacement or without replacement from a pack of 52 cards. So without replacement means two cards are drawn. Find probability that both cards are black cards. How many are black cards? Total number of black cards. How many are black cards? 26. Okay. So probability of taking out the two cards, card 1 and card 2, but without replacement. So then it will become probability of A intersection B this will affect to each other because they are asking find the probability of two cards means probability of two cards but without replacement. So first card is 26. We can select 26 out of 52 cards, and then for second card we are not putting back without replacement. So these are the dependent events. So this will become 25 by 52. 26 2s are 52. So 25 upon 104. Okay. So like this we will go. Generally we will have independent events in this exercise.
Yes, sir.
Yes, 51. Sorry. This one I forgot to make it 51. So this will be 51 because one card we have taken out. So 51 into 2. So 102, correct? So 25 by 102. But most of the questions you will find here, they are based on